a bit of a tight session. We might overshoot it by 5 minutes or so, hopefully not much more than that. So what we plan to do today is we will get started as always with the case studies. We have quite a few people who have written in. Thank you very much for that. And this question which was asked was on trigonometry and probability. And then post that, we will have a didactic, which we just termed it as Algebra-II. It's really a continuation of algebra from the previous time when we did algebra, which was more introduction. And this time around, we will do algebraic identities and quadratic and simultaneous, what do they all mean. And we have a lovely session by Bhama, which is on fun stuff. You will know what it is when you come there. And wrap up and feedback, which is really a buffer we keep. If there is a feedback, we will take it. Otherwise, it's really a buffer we have in terms of meeting the deadline of 6:30 close. All right, so we have plenty of case studies. We might overshoot the 20 minutes. Ruchi, if you're there, can you just speak up and say you're there so that I...
Ruchi isn't there, but there is Neeraj and Saujanya, and Namita is going to join now.
Okay.
Neeraj is there.
Neeraj, if you're good to go, we can get started, Neeraj.
Neeraj, can you hear us? Neeraj?
Yes, ma'am, I can hear.
Yes. Ramesh, I
so
think
before
Neeraj
you start, yeah, great. Before we start, these were the questions for the interest of everyone else. These were some of the questions we had asked, saying in terms of trigonometry, how do you introduce trigonometry to the students? And can we think of some concepts related to nature and trigonometry that will make it more beautiful and appealing to children? The idea is not here just towards learning. It's also how do you appreciate the trigonometric beauties which are in the spaces around us, and how do we introduce and develop probability and develop the idea. Regarding probability questions, I'm going to not take them. I will pass them, but right at the end, I will come and talk about some of the thoughts I wanted to share on probability, or more generally in terms of activities. I have a couple of slides on that, so I'll come and talk about it. Yeah, go on, Neeraj. Neeraj, go ahead.
Neeraj, your audio is off. Neeraj, can you hear us? I think we have Ruchi, Ramesh. We are not able to connect to Neeraj. We have Ruchi. Okay. Ruchi, can you hear us?
Yes, ma'am, I can hear, but I cannot hear you because I'm on the way. So after approximately 35 minutes, I will be able to.
Okay. Okay.
There is Saujanya. Saujanya, can you hear us?
Yes, ma'am. Can you hear me, ma'am?
Yes, we can hear you. Yes, you answered a few of the activity questions, right? Saujanya,
my question, ma'am?
Yes.
Yeah, ma'am. Hello, am I audible, ma'am?
Yes, yes, we can hear you. Do you want to say anything about the, can you show the slide? Yes.
Yeah. Yes, ma'am. So good evening, everyone. Happy Navratri, first of all, to everyone. So regarding probability, as it is a very interesting and simple concept, we introduce it to the students at the basic level. Firstly, when we proceed this with the activity, children show more interest to participate and learn. It is very simple to introduce with a coin or a dice. So as the probability is the possibility of an outcome of any random experiment. So for example, if you flip a coin, there are two possibilities, either a heads or tails to come up. And when we ask the student what is the possibility for a head to come up, and that can be measured through the formula, and when like the concept can be introduced with these two simple activities or with a dice also. When a dice is thrown, what is the probability or what is the chance of occurring a number 2 on the top face or a number 6 on the top face? I think with these two activities, the child may be easily understanding what is the need of probability in our daily life situations.
Right.
Thank you, sir.
Sajanya, when you roll a dice without us prompting, do children really end up with 1/6 as being the probability of any number coming up?
No, sir. No, initially not, sir.
Eventually, do they first give the answer before we say the 1/6?
No, sir. No, may not be, sir.
Okay. Because that's one of the things we have to remember in all activities. If you do an activity which will eventually have to be, the question has to be answered by us, then that kind of comes and brings to question in terms of what, of course, the activity has some role to play, but what role it really played is something we need to be mindful of. Because if the activity did, even for a coin, for a child to come up, so we'll have to probably use the appropriate expressions, because I think 50-50 is something which will come up in a classroom, but 1/6
Yes.
seems like a lot of stretch to come up with. So dice throwing activity might not, unless we prompt it and say, you see, there are 6 sides and one side, we are talking about one side, 1 divided by how many, 6. So like that, if you push it through, we can always get it to the answer. But if it has to be discovered by the class, dice throwing might be a little bit difficult, Saujanya, because that's something to keep in mind for you.
Yes. Yes.
Anybody else who's there? Neeraj, you said
Namita
yes.
is
And
there. Namita is there.
Namita, go ahead.
Namita, can you hear us?
Good evening, ma'am. Yes, I can hear you.
Go ahead,
Yes.
Namita.
There were three questions, ma'am, here. First of all, was to introduce the trigonometry to the students. So, I had written what I had done in the class, that they will be asked to see the angles around them and those angles making triangles, and how can we find them in the nature and around us, in our surroundings. So that thing, and the next question was, can you, and also we had done an activity on the swinging of the door, how it opens at various angles. So we had painted the floor in our maths lab like that, and that was one thing that we had done with the students of 9th class, and illustrated it to the lower classes, because painting was done by the 9th class, and it was used for other classes also. And the next question was, can you think of the trigonometry concepts related to nature? We had included nature there. So that I had just told. So, and how do you introduce probability and developing the idea? Probability में सर मैं थोड़ी सी खुद ही weak हूँ, लेकिन but I try my best uh, to introduce situations, and how, what are the chances of getting that situation, that particular desired result which we want, like you had just talked about heads and tails. So if you want tails, what are the chances? Or something else, if we are tossing a dice and we want a particular number to be displayed, like for opening up in snakes and ladders, and you want 6, so what are the chances? So how many are the total situations, and how many are the desired results? So that way we will go on with different situations and how we can go about it. So that's what we have been doing it. But I don't have a lot of teaching experience of probability as of now, because it's only been a year and a half for me in mathematics. But yes, we have done trigonometry a lot of times. Thank you.
Wonderful.
Hello,
You
hello, sir.
presented thrice in the last few sessions, and for someone who's 1.5 years into mathematics, really awesome. I mean, and don't worry about probability. Go back in case you missed the previous session. I don't know if you were there. There are methods in which we can introduce probability, because probability is one of those boo-boo areas where either we understand it properly or don't understand it at all. It kind of falls in that place. And once we get the right foundations, then it will automatically start flowing. Not to worry about that.
Sir, I would also like to share one thing with everybody here in the group, and I would like to thank the instructors here that I have been awarded the state level TLM competition third winner in Delhi. So
Okay.
so thank you very much for your guide, because a lot of sessions with you people have helped me, into the insight of how far I can go with a certain concept, whatever I choose, how far I can go. So that perspective, I'm really thankful to everyone here. Thank you so much.
Great, great. No, the effort is entirely yours, and yeah, we just catalyze the whole process to whatever extent we can. Thank you.
Absolutely. So that's what we do in the class as well.
Exactly. Yeah, yeah. Great. Any of the
Hi,
other
sir. Good
people
evening.
either? Yes, Rakesh, go ahead.
Yeah, sir, I want to say something about introduction to trigonometry. In my class, I used a very basic concept. When students are sitting on their bench, then I'm showing a trigonometric example after sitting on their bench. I told the students, look your book, and after that, look on the board. Okay, between in both process, if you will see the your book, then you will take a angle from that point to your eyes. You make an angle of elevation, and if you will see on the board, then you make an angle of depressions. Okay,
Nice way.
and
Very nice.
it is very simple process, and the students is very quickly understood their positions.
Yeah.
And after that, sir, I give some example. For example, find the value of some trigonometric relationship like this: 32 upon sec square theta minus 20 upon 1 plus 10 square theta, like that, and up to so on. Then I just said that check the difference. The numerators 32 and 20 is 12, and if I add another trigonometric ratio 12 sine square theta, then we check a relation with some specific trigonometric signs. If the difference of numerators with is same that like third trigonometric symbol, coefficient of trigonometric symbol is 12, and in this case I use sec 0 degree. Sec 0 degree is equal to 1, tan 0 degree is equal to 0, sin
Yeah.
0 degree is equal to 0. It's
Yeah.
very simple process, and the students give the answer quickly in 5 to 10 seconds.
Awesome.
If you can write it out, then it will be nice, because I'm not able to understand clearly.
Yeah.
Next
Yeah.
time, if you can, yeah.
Ma'am,
Correct. Rakesh, you should.
I can
So it will help in our planning also, because your thoughts are important for us to be shared in the group. You should take 2 minutes out to write the cases, because we keep following up as well. If you can put it there, it will be really nice, Rakesh. Yeah, we can move on to Saujanya, if you're, sorry, Saujanya is done. Neeraj, if you're there, or Ruchi. Ruchi said it'll be a bit late.
He said network issue. Neeraj said he has network issues.
All right. All right. Okay. So we'll press on and go into something I wanted to kind of talk about. See, in a more traditional way in which we used to be teaching mathematics, the process was simply this. There is a question, okay, or a question which the teacher apparently assumes is important to the students, and then she or he give out an answer and say, this is how you solve it. And there's a lot of hue and cry saying that, what are we really doing? We're just creating some artificial questions. It might be very important in life, but how will the students really learn? What is the whole point of having a question and an answer and a question and an answer? You're just stuffing them with information, and having a lot of information is not going to get very far. And we have to resolve this. Then we resorted to this whole idea called an activity. So we inserted between the question and the answer an idea called activity. So some of the activities which we do, whatever that particular activity might be, so which could be rolling a die, what I was asking Saujanya, do the children really come back and tell you that the probability of getting a 1, forget the word probability, the chance of getting a 1 in a roll of a die is equal to 1/6. It's very difficult for the children to really reach there unless we actually give it out and say it is 1/6. So what the activity does, right? While it's good to have an activity of 2 or 2, it doesn't change the texture of learning itself. The learning earlier, which was going from a question to an answer, is now having something in between, which is an activity. And then after that, we have kind of checked one more box. Earlier, we were checking 2 boxes and said, did we ask the question? Yes. Did we answer the question in the class? Yes. Now we have made it into 3 tick marks: question, activity, and answer. But it still doesn't change the texture of learning at all. The learning is still passive. The learning is still something where the teacher is sharing her knowledge with the children. And it just goes on like that, where the students have become passive recipients of information and knowledge. And there is no engagement which happens. And there is no curiosity, there is no engagement, there is no discussion which really happens. Yes, there might be a discussion. So I don't want to dramatize. I mean, I don't want to take it to an extreme. Yes, there might be some discussions, but an activity has to be much more than some kind of an introductory business which we do before we get to the topic straight away, as a chore which we have to complete before we go into the topic. Now, what do we really mean by that? Okay. Now let's go back. I'm not saying this is the right game, but I want you to go back and think about one game we had introduced during the last session. The game goes something like this. The children are seated in a circle. The first kid has a die in her hand and she rolls the die. Every time she rolls a die, she gets a candy. If she rolls the die again, she'll get one more candy. If he rolls it the third time, you'll get a third candy. But there is a problem. The problem is, if one lands up, then not only do you have to pass the turn to the next child, you have to give all your candies. Okay. Now, what happens in this game? You roll the die once, you get the number 4, which means you get the candy. Now the child has to make a decision. Do I pass wherein I'm happy with that one candy? Or do I take a chance and roll it one more time? And if I get the number 5 probably, or 3 or 6 or whatever it is, I'll get one more candy. I double the number of candies I have. So the child might say, okay, let me roll it one more time. And let's say luckily she gets 5 and she gets a second candy. Now she has to think in terms of, will I roll again? Will I not roll again? Okay. Now, these are some of the conflicts the child is going to go through. There is a certain, we don't know what the answer is. We don't even know where we are heading as an answer. Okay. But you can just imagine what will happen in a class. You roll a die, you get a number, you actually give a candy. Physically, you give a candy. You roll the die again, the number is not 1, you give the second candy. The child has now collected, let's say, 7 candies. And then she rolls and gets a 1. We not only ask her to pass the die to the next person, we take away all the candies, all the 7 candies. You can just imagine the heartbreak the child will be going through when you take away all the 7 candies she has earned. Only in that round, not in the earlier rounds. Yeah, only the candies which are earned in that particular round. So then somewhere along the way, the child is contemplating and saying, maybe if I get 2 candies, I should just pass and I should be happy with it. When we raise the problem a little more engaging way in the classroom, words like luck, greed, and things like that might start surfacing in the classroom. Somebody will say, I don't want to be greedy, but is there a right answer? Is there a point at which you should pass? Or should you keep rolling infinitely? And what is the point you want to pass? Okay. Now, this is an introduction to probability. What exactly in probability are we introducing through that? We don't know. We are introducing to some extent gaming and strategy, okay? But we are not exactly introducing it as saying that it is gaming or strategy. We're just playing a game, and that game has got elements in it which is making something happen in the classroom. It is making something happen not just in the classroom, it's making something happen to all the children in the classroom. All right. So this is something which happens. There might be an exact answer. There might be an exact answer, which is the probability of getting 1 is 5 by 6, and the probability of getting 1 twice is 5 by 6 squared, and so on. But that's not important. It's too early to bring about any discussion on probability. There might be an exact answer. Okay, but we don't want to get to the exact answer. We want to get to an answer where children, after playing this game for about 45 minutes, kind of figure out there is a point at which they want to give up and pass the die to the next person and say that I'm happy with this. I'm happy with the 3 candies I've earned, or 2 candies I've earned, or 1 candy I've earned, or 4 candies I've earned. I'm happy with this, and I want to pass the die to the next person, in which case you keep the candies. So you get a 4, you get 1 candy, you get a 3, you get 1 candy, you get a 5, you get a candy. Now you got 3 candies. You can say, okay, I'm done. I pass my die to the next person. So through the process of trial and error, the children will figure out an appropriate strategy. Okay. Now what we are appealing through that particular activity, which we have fitted between the question and the answer, it's very, very important to have an activity. But the activity has to have more elements than just being an activity, which is a check mark where we say, okay, the question done, activity done, answer done. Instead, it has to do a lot more than that. So between the question and the answer, there clearly is an activity. Now that activity has to have many, many elements. I've listed out a few elements. The elements which I've listed out are, there has to be a sense of wonder. What is going on? Should I give up, not give up? Okay. There has to be a certain struggle the children are going through, saying, where do I give up? Because if I give up too early, I get only 1 candy. If I keep waiting too late, then number 1 lands up. Then they figure out through a trial and error. They see and learn from other children, saying somebody who gives up at 2 or 3 seems to be making more candies than other people. They will have to fail. There is a certain curiosity which gets raised in the class. The class starts thinking together and saying, what should I do in this game? And then the breakthrough comes through from the class, not from the teacher. From the class, a breakthrough comes through. There is a process of discovery which happens, and there is awe, joy, and finally satisfaction. If an activity contains all these elements, these are just words, really. Don't get stuck with these words, whether it's 8 or 10 words which I've put out there, but just think about our activities through this kind of a process. Is it able to create a sense of wonder? Is it able to create some struggle, some curiosity, some trial and error and failure and thinking, and where when they break through, there is a sense of joy and awe and happiness and satisfaction? If all of those happen, then it's a good activity. If all of these things don't happen, but a part of them happen, it's still a fine activity. But if none of these things happen, it is just that something got introduced through a process which is called an activity, then it is not really an activity in that sense. It's an activity, technically speaking, because we physically showed something as compared to just writing it on the board, but it's not truly an activity if it doesn't evoke. Ultimately, what we are coming to is saying learning has to be a very emotional process. Math learning has to be an emotional process. An emotional, if you look at each of these things, wonder, struggle, trial, failure, curiosity, thinking, breakthrough, discovery, awe, joy, satisfaction, every one of these is an emotion. Right? Except probably thinking to some extent is not an emotion, but thinking is also an emotion in many ways. So what we want our activities to really do is for the children to start emoting with the whole topic itself. If the children start emoting with the whole topic, along with us as a teacher who can act as a catalyst, then great discovery can happen in a classroom. Otherwise, activity will just be a chore which we will complete before we get to the good old drab of solving equations and processes and procedures, and we will not solve the most important question we started with in Reimagine Math, saying, how do we reduce math anxiety? How do we stop our children from saying, I hate math? Right? It has to have all these elements. Just bear this in mind before, whenever you're devising any activity, just keep these elements in mind and try and figure out some activity which will at least have 6 or 7 of those elements, so that the process of learning becomes really emotional. Yeah. And yeah. So with that, we will move into the didactic for today. The didactic for today, like I said, is Algebra-II, which I will cover. In the previous algebra, we said a few things. One, we said introducing the idea of an unknown or the concept of an unknown is critically important. Because when they come to algebra, they have completed arithmetic, all the children. They know the 4 processes of addition, subtraction, multiplication, and division. And suddenly we are going to land them in a very different kind of a place. And the idea of an unknown has to be very, very important and a very crucial step. Even in introducing the unknown, I don't want to rehash whatever we went through. We can, even when we are introducing notations, just use notations as if it's just a placeholder on the right-hand side, how arithmetic works, right? In arithmetic, we would have done a problem like 4 times 5 plus 2 equal to 22, and just put an X or a Y or something there at a later point in time, whenever we are ready to bring the variables. Of course, we know between the unknown and introducing a variable, there are multiple steps in terms of games, which we have covered in Algebra-I very adequately. We don't really want to talk about the variables. It's just to be thought of as a placeholder where it can enter our conversations as we move into it. Okay, the class activity pebbles we all saw. The second thing which we talked about in Algebra-I is it is impossible to really do good algebra or good geometry without understanding the relationship between the two. And there are 2 quotations which we talked about, which are very powerful. There are many, many quotations on algebra and geometry. I quite liked these 2, one by Lagrange and the other one by a lady called Sophie Germain, which is algebra is but written geometry and geometry is but figured algebra. And the second one, Lagrange, is very, very interesting. As long as algebra and geometry have been separated, the progress has been slow and the use is limited. But when these 2 come together, when they unite, they have lent each other mutual forces and have marched towards perfection. Okay, the entire space of calculus and everything else integrates it. There are many other areas where it gets integrated. Algebra and geometry are pretty much joined at the hip, and we should not be thinking of these things as separate topics, which then means that whenever we write equations in algebra, we should have opportunities to visualize it. When we draw a simple line like this, what does it really mean? What curve is this, or what equation is this? When we move that curve a little bit steeper, what does it really mean? What happens to that particular, when I use the word curve, I mean, pardon me for using the word curve everywhere, I'll use it for a straight line as well. So not necessarily for only curved lines. So when you draw a line or a curve, what does it really mean? So what does it mean when the line looks like the other way around? It is sloping this way instead of sloping that way. And these are some conversations we want to be having in the classroom. Okay. And the next step is really, okay, to ask this question, what happens to y as x increases? What happens to y in the first case? What happens to y in the second case as we put values of x equal to 1, 2, 3, 4? What happens to, and what happens to y in the second case? What happens to it? Okay, as we are increasing, what happens to y? And then we can further visualize by saying, if this particular orange line is, y equal to x minus 3 or 1x minus 3, what can we really say about this green line? Okay, we should not really try to solve it. We should just be able to look at the green line and say, this is what it is. because we know the green line is a parallel shift, which means the 1x is not going to change. And it has just shifted a little bit up in some sense. And therefore, it's probably a x plus 2 or x plus 4 or something like that. And that is probably what it is going to be. Okay. And if the orange line is this, what can the blue line be? So these are the ways to imagine. These are ways in which we want our children to imagine. And what will 3y equal to 3x minus 9 line look like? And we should actually draw it and see what does this line look like before we start introducing simplification of a certain thing. As all of us as adults know, this will equate exactly to the x minus 3 line, but it will be quite an interesting discovery. Okay, so those are the things to do in Algebra 1. Okay, we have to have good mastery over visualizing, idea of unknown, very, very comfortable with the idea of variables, and quite happy to juggle and move around variables, whether they're stuck on the left-hand side or the right-hand side of an equation, and have the ability to manipulate it. Once we have done all that, then is the step which we're calling as Algebra-II. Algebra-II has really got 3 elements in it, which is simultaneous equations, polynomial expansions, and quadratic equations. Okay, what do we mean by simultaneous equations? Why is simultaneous? When does it really happen? Now, in the field of economics, an opportunity cost is what is that I need to forego to get something. If I have a certain amount of money and I want to buy a car and I also want to add a bedroom in my house, but the amount of money I have is only equal to the price of a car or adding a bedroom, but not for both. Now, if I add a bedroom, I have to give up buying a car. If I want to buy a car, I have to give up adding a bedroom. And there are many, many situations in the field of economics, in our own personal finances, where we have to make choices. Where we have to make choices in the sense, with the limited amount of resources I have to choose either A or B or a combination of A and B, but not all of them. How do I get those combinations? What is that will work for me? Okay, that is when the simultaneous equations come in. This context is important. Now I have 100 rupees. Okay, I could either buy 5 apples, each costing 20 rupees with it, or I could buy 10 bananas, each costing 10 rupees. I could do either of those two things. I can buy 5 apples, or I could buy 10 bananas. But I could also do something else. I could also buy, saying, I don't want 5 apples, but I want some apples and some bananas. Why don't I buy 4 apples? In which case, I will have money left over for 2 bananas. Or I could buy 3 apples, and I'll have money left over for 4 bananas. And then I can mix and match. Okay. But can I buy 5 apples and 10 bananas? No, I can't. Why? Because I have only 100 rupees. Unless I have more money, or the price of an apple or a banana goes down, I won't be able to afford it. So in this particular example, where we have 100 rupees and the apple indeed costs 20 rupees and the banana costs you 10 rupees, then we have to make choices. So the choice is, I want bananas, I want apples, I want to have the cake and eat it too, is the kind of situation, is the kind of predicament where we have to solve for it simultaneously. I have to simultaneously think of whether I want apples, whether I want all apples, all bananas, or a combination of apples and bananas. If so, what are all the various combinations I can get? That is at the core of simultaneous equations. So when we talk about simultaneous equations, take up a problem of this nature that I have. So we are not going into any X or Y or A or B or anything else. So we just take a problem like this and say, I have 100 rupees and I want to buy this. And then slowly we can develop the problem. How do we develop? Okay. So for every extra apple we want to buy, we have to give up 2 bananas. Okay, or the way I described it, for every banana we want, we have to give up every 2 bananas we want, we have to give up an apple. So the process of planning and budgeting any mix lends itself nicely to simultaneous solving. If I increase one, something is going to give. If I increase the other, something else is going to give. And what I have to do is simultaneously look at all these things and solve for it and say, what is my quote unquote optimal solution? An optimal solution is something which will satisfy my need within the overall budget which I have. If my need is this, that I want 8 fruits, come what may. Okay, what are all the different ways and combinations I could buy this? I want 8 fruits. Forget the 100 rupees now. I just need 8 fruits. What are the different ways I can buy them? So the answers very clearly are, I can buy 8 apples and no bananas, 7 apples and 1 banana, 6 apples and 2 bananas, 5 apples, and so on and so forth. But I need 8 fruits. Okay, maybe there are 8 people I need to give it to, and they're quite agnostic whether I give them an apple or a banana, but they're going to be very unhappy if I don't give them a fruit at all. In that situation, then there are many ways in which I can buy the fruits. But what if, okay, I have both those issues? I need 8 fruits and I have only 100 rupees. And I want to use up all my 100 rupees. So I want to pay exactly 100 rupees and I want exactly 8 fruits. Now, what have we done? We have created a problem which has to be solved simultaneously. If I look at only one side of the problem, which is 8 fruits, I can say I'll buy 8 apples. But you know what? 8 apples is going to cost me 160 rupees and I'm out of pocket. I can't do that. Okay, I'll buy 8 bananas. But then you end up spending only 80 rupees. You have to spend 100. Okay, for 100 rupees, I can buy 5 apples. No, but you need 8 fruits. Okay, I'll buy 10 bananas for 100 rupees, but you have to have only 8 fruits, not 10. Now, that is where it becomes simultaneous. Unless we think of both these problems together, we do not arrive at a solution. So the solution at which it satisfies both those conditions of 8 fruits and 100 rupees is where it simultaneously solves both of those things. Okay, where we want exactly 8 fruits and spend exactly 100 rupees is where we call it simultaneous. That's how it gets its name, saying there are 2 things and I have to solve them simultaneously. Next step is obviously we get into a graph, because geometry and looking at it visually and algebra are very, very important. And we can start off by saying, okay, if you need 8 fruits, what are all the different combinations I can buy at? Okay, for 8 fruits, I can get various combinations. I could get here 6 apples and 2 bananas. The apples are there in the y-axis and the bananas in the x-axis. It could be 6 apples and 2 bananas, 5 apples and 3 bananas, 4 apples and 4 bananas, and so on and so forth. And what are the different combinations of spending exactly 100 rupees? The different ways I can spend exactly 100 rupees are, I can buy 5 apples, 5 into 20, 100 done. Or I can buy 4 apples and 2 bananas. So the point 2, 4. Or I can buy 4 bananas and 3 apples, the point 4, 3. Okay. And these 2 lines, the blue line and the orange line, meet somewhere. Where do they meet? They meet at a point where it is 2 apples and 6 bananas. What's the total number of fruits? 2 plus 6 equal to 8. And what's the total cost? 2 times 20 plus 6 times 10 equal to 100. And that's it. They're simultaneous, they're solved. There is nothing more to simultaneous equations than this. We have to understand what is that we are trying to solve simultaneously, where we don't want to answer on only one or the other, but we want an answer to stick on both of those things. And wherever they solve themselves, by drawing those 2 lines, wherever they solve themselves, then it is simultaneously solved. because every point along the orange line is 8 fruits. And every point along the blue line is exactly 100 rupees. So wherever the orange line meets the blue line, it's automatically 8 fruits and 100 rupees. And that's all that is there to simultaneous equations. Then we can get into some discussions and say, what is that which happens in the orange space? What is that which happens in the blue space? And what is that which happens in the space where it is both orange and blue? The shaded area, where it is shaded only orange, where it is shaded only blue, and where it is shaded both orange and blue. These are conversations we can have as a classroom, and we won't cover it here, but these are very, very useful conversations to have. And we can also go on to ask what happens in the white space, which is above all of these things, which is neither shaded, which is not shaded orange or blue or orange and blue, but the white space, which is to the right side. What happens in those spaces? What if I take a point there, which could be 6 apples and 11 bananas or something like that, take a point like that, what will happen? I will have too much fruits as well as I have to spend too much money. So this conversation will get us to a place where we can have the simultaneous equation. The rest of simultaneous equation is really a process. 2x plus 3y equal to 7 and everything else. Multiply the first equation with another number and subtract one from the other, eliminate one variable, divided by this, rearrange. All of that is the process, but we will be able to do the process very, very easily if you have understood what simultaneous equation is all about. Right. He said there are 3 things: polynomial expansion, simultaneous equation, polynomial expansion, and quadratic equations. In polynomial expansion, we will go into a plus b whole squared, which I'm told many of the teachers do as well, which is take a sheet of paper and mark out some number. A could be 7 centimeters and b could be 2 centimeters, and mark out some number. And we know this yellow space is nothing but a square. And then this little blue space is a square of side B. Why is it called B squared? Because it's a square, that's it. Because the shape is a square. The shape is a square, it's a square with a side B. And the area of that is B square. And what are those black areas which have now turning green? And one side is A, other side is B, therefore the area is AB. And the other black is also AB. So a plus b whole square is nothing but a square plus b square plus 2ab. This can easily be done as a paper cutting exercise. And the same paper cutting exercise, in fact, for a squared minus b squared is very beautiful. Okay, even a minus b square is quite interesting. Please do try it out in your classroom, and those are very nice. The one I particularly like is a plus b whole cubed expansion, which is very, very beautiful when it is done as a physical model. Because very often when we write the terms a square b and ab square, okay, they look almost similar. Each one of us in our class, at least I've had this confusion. When somebody says a square b or ab square, it looks like, okay, there is there is a b, and there's a 2 upstairs somewhere. What difference does it make whether it's a square b or b square a? I mean, they all look pretty much the same thing only. But when we visualize it as an object, they look very, very, very different. Okay. So a minus b whole square, I'm not going to take too much time. This is very nice. A square minus b square looks like this. So there is a square. From that, we cut out b square. And then what we do is we take this little strip, the green strip, and attach it to the bottom. We cut it out and attach it to the bottom, which makes it one side is a plus b and the other side is a minus b. So which means a square minus b squared is nothing but a plus b into a minus b, which we are all very aware of. Okay, so let's take a look at a plus b whole cube, how it looks like. Created some animation, hopefully it will flow. If not, yeah, it's flowing on its own. So this whole thing is a plus b cube. And we have a little cube which is orange color. And there are 3 cuboids. Each of them are b square, which is the face, and with a length a. And then we have a square faces with length b. And you put it back together, we get a plus b whole cubed is nothing but a cube of dimensions a. And then we have 3 of those cuboids which have dimensions of a square and b, and 3 cuboids of dimensions b square and a length, and we have 1 cube which is b, and that's polynomial expansion. So when we get into polynomial expansion, very similar to some of the earlier topics in mensuration we were talking about, the best is not to have too many formulas. It is okay to have the formulas, but the children should feel that it is the kitchen knife they have. The kitchen knife will not cook you the meal. It's a very important tool to have, but I cook the meal. I'm the boss cooking the meal, and the kitchen knife is there to help me. The formula is there to help me, and the formula is not the one to which I pray to. Okay, the formula is something because I know how I can do it logically from first principles, which means the formula is something which I will use as a tool tactically to solve a problem because it's convenient to do that, not because the formula is a gospel truth which I have to pray to. And that's very, very different in terms of the approach we have towards a formula. Formulas are very important, but let's not give it a place which is higher than ourselves when solving mathematical problems. Which brings us to the last topic of my topic, which is quadratic equations. Quadratic equations, again, is somewhat similar to simultaneous equations, only that the problem structure is a tad different. Okay, what does the problem structure look like? What happens is, in the earlier case, we said, X apples and Y bananas and everything else. Here, we express one as a function of the other. Those are quadratic. What we are saying is the length of a table is 5 more than the breadth. Okay, so tell me what is the breadth? I don't know. Okay, at least tell me what is the length? I don't know. But I can tell you whatever the breadth is, the length is 5 more. But I neither know the length nor the breadth. But I can tell you this much. If I measure the length, whatever the length might be, so it could be a 15 and 10, it could be 18 and 13, it could be a 12 and a 7, it could be a 10 and a 5. All of these are okay, but I don't know what it is. But there is another clue. The second clue is the area of this table is 150. Again, best to be solved through trial and error process. Okay, the class will be very easily able to answer this question, and they will quickly come up and say the breadth is 10 and the length is 15, and that pretty much solves it. Okay. So what are the sides of the table? It is very, very important that some problems like this are structured, which is my brother is 3 years older than I. And the product of our ages is equal to 24. What is my age? What is my brother's age? Okay. Any place where we express one as one unknown as a function of another unknown, it will lend itself quite neatly to a quadratic formation. We can structure any number of problems like this. Okay, we can structure any number of problems like this, but it's better that multiplication has some sense. The product of my age and my brother's age is equal to 24. It doesn't have as much sense as the area of this table is 150. So you just have to see that whenever you multiply, it still has some meaning left. In this case, the area is a very meaningful idea. The product of two ages is not that meaningful an idea, but what will be a preposterous idea is the price of dal is 50 rupees more than rice, and the product of their prices is equal to 1,500. Makes no sense at all. Okay, so just be careful when you're structuring problems like that, but do go ahead and structure that. And then as we get into tougher and tougher and tougher problems there, then the need for the tool is felt. And that particular tool is what we are calling as a quadratic equation. So we can start visualizing the earlier problem where the area is 150, length is equal to breadth plus 5, which means length times breadth, which is b plus 5 into b equal to 150. So b squared plus 5b equal to 150. And we can write out all those numbers. What if b is 1 or 0 or 2 or 3 and everything else? How much is b squared? How much is 5b? How much is b squared plus 5b? And we can slowly start visualizing. Not in this problem. This problem, the class would have solved it. Okay, quite easily the class would have solved the length equal to 15 and breadth equal to. I'm taking that as an example. But when we come to a tougher problem, we can get into this table and visualization. Once we get into table and visualization, and as a graph also, we are able to visualize what a quadratic equation looks like, then we can get into formalizing the process. Now, how do we formalize the process? Again, we resort to that same old table only. Okay, only that the table will now be a square. So if you take an equation like x square plus 4x equal to 45, the first thing we do is draw a square of side x. How much is x? We don't know. It's just some x. We are drawing a square, which is x squared. To that, we are going to add the 4x. We know the side of the square is x. So if I put two little rectangles here, okay, one on this side and one on that side, then I have two rectangles, the areas of which are one side is x, the other side is 2, the area is 2x, and the other one is also 2x. Now this shape has a total area of x squared plus a 2x plus another 2x. So x squared plus 4x, which is nothing but the left-hand side of our equation, and that total area is equal to 45. But it's not very interesting enough because there is one little notch which we have in the top right corner. Let's just fill it up. And we know the two sides of that are 2 and 2 because that's how we have taken those rectangles. So which means we are adding that to our left-hand side. We are adding a tiny little square of sides 2 and 2, which we add to the left-hand side. So the right-hand side also, we have to add 4. So 45 plus 4 makes it 49. And this whole square is nothing but a square of dimension of area 49, which means every side is 7. And we know the height of the LO is 2, and therefore x equal to 5. That's it. Right. So this is what quadratic equation is all about. So where did we start? We started off by formulating problems where we have two unknowns and one unknown is expressed as a function of the other, which is the table example we took. And then we visualized it by drawing a table of the whole thing. We visualized it also in the form of a graph. And then we tried to formally solve it by creating some equation and then solving it by completing a square. Once we have done all that, now we know what quadratic equation is. And once we have got this intuition, the rest of it is straight away, we can get into visualizing something and get into the formal process of solving a quadratic equation itself. So whenever we visualize a quadratic equation, we take any quadratic equation like x squared minus x minus 12 and actually plot it. Then we will see these quadratic equations are very different from what we saw in Algebra 1, which is all about straight lines. And the second thing is these curves seem to be dipping and then rising and going up again. And all those imaginations will be there in the mind of a child. And not only does the quadratic equation cut the x-axis once, it invariably cuts it twice. At least in high school, they will definitely cut it twice. Otherwise, there is no solution for it. And in the high school, every equation we will see in our textbook will cut the x-axis twice. Okay. In some rare cases, it will only touch it and go out. And we will be able to do all those things. Okay. So in summary, all we are saying is simultaneous equations are essentially straight lines where we have a problem of opportunity cost, where we have to give up something to get something. And when we have a problem like that, we need the solution to solve both of them simultaneously. In quadratic equation, where one is expressed as a function of the other, and therefore it will lend itself into a curved line, which will typically have two solutions. Okay. not necessary. I mean, so, but will typically have two solutions. It can have 0, 1, 2, whatever, but it will typically have two solutions. And polynomial expansion, where the key thing is we don't end up mugging what is a plus b whole squared and, a plus b whole cubed and a squared minus b squared and all that. We have a process of visualizing. And therefore, when we actually come to the formula kind of subordinates to us rather than it is sitting on a high horse and we all pray to it. Yeah, that's it. Did I take a lot more time than what was scheduled for me? No, not too bad. I actually finished
perfect.
on. Yeah, I actually finished. I somehow thought I was way beyond time, but I didn't want to check my time because I wanted to. This is one topic I really like.
Exactly 6 o'clock. So
yeah, beautiful.
So nice. Yeah. Really so nice. Yeah.
Okay. Now over to Bhama for some fun stuff, the next half hour. Before we go there, Ruchi, are you there?
Yes, sir.
Okay, I'll go straight to your case and then we'll come to Bhama's. Yeah.
Ramesh, it was very interesting the way the banana apple example itself, and then can we use the same example to talk about what change in the question would make it a simultaneous equation and what change would make it a quadratic equation?
Yeah.
So it would still be one thing and you would be able to cover a lot of ground with the same example. Yeah.
Yeah.
It's just fascinating. It's
yeah.
so nice. Thank you.
Yeah, just one thing, if all of you can just keep a piece of paper ready with a pen, just if you have something to write down for the next session.
For Bhama's session, please keep a piece of paper and a pen next to you.
Just for some simple drawings, yeah.
Yeah, for some simple drawings, yeah. Ruchi, go ahead.
Okay. So the first question was how do you introduce trigonometry to the students? So basically, trigonometry is usually sounds like meaningless or usually is like something which is not implemented directly in the environment. Usually what teachers and students says, this is what their perception I'm trying to reveal here. So what I felt is that basically we need trigonometry to be shown in relationship to the environment, and where we can talk about the Gauss story of it while introducing, and then we can talk about with the unit circle concept, and we use this concept in a place where we were going with the curriculum, and we use this unit circle concept and we introduce trigonometry in terms of trigonometric functions rather than talking in terms of trigonometric ratios. And there in SOSC schools, certainly some schools was very exciting results, and initially the teachers were not ready to accept it, but those who accepted, they were very excited with the results, and then they shared that with us. Yeah, that how the different measures or different angular measures students were able to find out in terms of sine 60, 70, 90, 120, even they were able to, and they were even able to relate sine cos with that unit circle. And with that, the students even were one of the teacher quoted and showed us the video also that students were able to find the height of the trees, whereas other teachers said that they were able to find various heights in the school building. Can go ahead with the students, and then trigonometric concepts, when we talk about I think the height of trees, we can talk about height of long buildings, we can talk about shadows, relating it with the shadows and the buildings or pillars, we can talk about. And recently one of the examples clicked to me was like we can talk about jantar mantar also in this respect, where right triangles are very prominently there, and the trigonometry and coordinate is very much embedded there in that system. And
Yes,
last one is how do you introduce probability and develop the idea? So tossing a coin is of course easiest and interesting because Kids play Ludo, and dice today are used in various areas of number system also. So it's a familiar thing they can go with. But on the contrary, again, as you have introduced, that we need to add some more inputs in that. But from there, we can go with various things that will it rain today, or which color is more liked by the students. And the spinning wheel is always a fascinating process in the classroom among kids. So we can go with this activities while introducing. And of course, we can talk about the outcomes and events with these lines. Thank you.
Ruchi, ma'am, what is Gauss's story for introducing trigonometry, please?
Right now, not the whole story is in my mind. I just remember that Gauss was looking at the structure, and he was thinking how we can find the height and its relation with its shadow. And there he worked with this idea of trigonometry, and he used that, and that right triangle he used to find out the relationship between the shadow and the tall building. And initially, he started observing that what could be the ways I can find the height without without exactly measuring the height.
That will be more on ratio. I mean, end of the day, they're all related, but
Yeah.
that's a more classic one on ratios. Taking any known object and then measuring the length of the shadow, measuring the length of the shadow of a building, and to estimate or exactly find out the height of a building. That's but the idea of an angle is something which is critical to trigonometry, which we can also, I mean, we can always think of, where is the sun ray coming at what angle and all that. They are related, but it's a more classic exercise for ratios. Great. Thank you, Ruchi.
Thank you.
Yeah. So there was something we talked about regarding activities. So if you have some time after the session, please go through that as well in terms of activities. So some of the elements which we should try and have in activities. So that's something to keep in mind. Yes, Baba.
Yeah. Yes. Thank you. Thank you, Ramesh. So today this didactic will be in two parts. The first one is an introduction. Okay, I'll just start off. Yeah. So the 7 bridges of Königsberg. It's like a historically very famous problem in mathematics. So in Russia, there is a town called Königsberg, and it is situated very close to the Pregel River. And this river, it splits and it forms an island and a peninsula before it reaches the sea. It's shown on the right. So, and the town is spread on either side of the river, over the island and the peninsula also. And it has 7 bridges to cross the river at different points. And this is shown in green. And the challenge posed was this: can we devise a walk through the city that would cross each and every one of its bridges once and only once? Through the town, you can go any number of times, through the island or through the peninsula or the either side. But then the bridges should be crossed only once, exactly once. So Euler, the Swiss mathematician, he was given this puzzle to solve by the king of those times. So his intuition was the physical map doesn't really matter. So the areas of the regions of the city, of the town, of the island, the areas don't matter. Only the connections between them matter. So basically, we have this list of regions that are connected by the bridges. So he came up with this abstraction. He represented every region by a node, each region by a node or dots or vertices. and the bridges are arcs that are connecting the nodes. And such abstractions we now call them graphs. And so here there are four distinct regions, right? So A and B are on either side of the river. C is the island and D is the peninsula. And so these are represented by the vertices A, B, C, and D. And these regions, they are connected by bridges. So between A and B, there are two bridges, A and C, sorry, there are two bridges, P and Q. Between A and D, there's a single bridge that is U. And then between C and D, there's a bridge called T. C and B, R and S are two bridges. And between B and D, there's a single bridge V. So this we can draw as a graph as shown on the right. So the challenge now is to start any vertex, trace out all the arcs only once, exactly once. The vertex can be visited more than once. So Euler proved that this problem had no solution in 1735, and in doing so, there were no suitable techniques in mathematics to solve this. So he came up with tools, and it led to a whole new introduction of a new field in math. It was called graph theory. And this has very wide applications in chemistry, in social science, in different varied fields. We'll see that later. So a graph, it looks very simple. It's just a set of points like vertices, and it has a set of lines, edges connecting the vertices. And what is very special about graphs is, and what is very different from Euclidean geometry that we know till now, we teach children even now, we start off with that, is that the edges can be curved or straight, the vertices can be rearranged in any manner, the length of the edges, it doesn't matter, the graph is still the same. So all the 5 graphs shown on the right, they all represent the same graph. It doesn't matter how we move the vertices and the edges around. It's still the same graph. And that was a whole new idea, a concept, which has so many applications. We'll see. And this game, even I have played it when I was small. It is like, it's a pattern of dots we connected by edges, like a traditional rangoli or kolam. And all we have to do, the challenge is you have to trace out this pattern without lifting your pencil from the paper and not going over any line twice. So if you can just take your paper and a pencil, and then you can try out all these different 1, 2, 3, 4, all these 8 different very simple graphs, and tell me whether you can start at any point, and you have to trace, you can go through any vertex any number of times, but all the lines should be gone over exactly once and only once. And if you come back to the same point, it's called an Euler circuit. Otherwise, it's just called an Euler path. So we'll just, for 2 minutes, we'll just and yeah, we can just wait. And if you can message in the chat, which are all possible, like, is one possible? I think one is straightforward, right? Is 2 possible?
Is the question clear for everyone? The question Bama is asking is that you can start at any vertex. If you take the figure 1, you can start in any of the blue dots, and you have to complete that without lifting your pencil. That particular shape without lifting your pencil. So you might want to just say whether 1 is possible. That is just to find out how many of you are actually trying it.
Yeah, 1 is possible. 2 is possible if you start at a particular point. Yeah, if you start at that particular vertex, 2 is possible. And if you can try it out, 3 and 4, do you think it's possible? 3, I think, is not possible. You will either miss out a line or an edge, or you'll go over it 2 times.
Shaili says 3 is also. Can you show us the picture, Shaili, if you can keep your video on and show? how 3 in your view is possible?
Just a minute, sir.
Take it up.
I started from. Can you able to see me?
Hang on.
And my notebook too.
Yeah, show your notebook.
So I started from A. So move. Sorry, this is A. A to B, then C, then.
We can't see your paper, ma. Can you show your paper closer to the camera? And then try and trace it. Yeah.
Is it
and
fine
trace
again?
it with your, yeah, trace with your finger now.
Okay. I started from A, then moving right.
Yeah.
Then diagonally, I'm moving diagonally again towards A.
Yeah, got it. Keep going.
Then moving to again right.
Yeah.
I think I left the rightmost
Yeah.
side. Yeah,
Nice.
you're right.
Yes.
Yeah. So yeah, if we if you have more time, we can try it out. But then, yeah, 3 and 4, it's not possible. And then, but 5, 6, 7, and 8 are possible. Yes, I think they should be possible. And these you can ask the children. These are nice activities to ask the children. If you come back to the same point, it's a circuit, otherwise it's a path. And yeah, so why this, yeah, next slide, please. Yeah, so why this is it's got a very simple proof which even children can understand, you know. So that's why I just wanted you to try it out. And when you try many things, you yourself will be able to understand why certain things are possible and certain things are not. So Euler also came up with a very simple method. And before that, just a little bit of terminology. So we call a degree of a vertex is defined as the number of edges that are attached to that vertex. So an odd vertex is a vertex which has odd number of edges attached to it, and an even vertex is when there are even number of edges attached to it. So now if you look at figure 1, right? So we ask the children, we give them these 3 figures, and then we ask them, what is the start vertex and how many vertices with even degree, how many with odd degree. So the first one has 1, 2, 3, 4, 5, 6, 7, 8 vertices, and all of them have 3 edges connected to them. So all of them are odd degree vertices, and we find that an Euler path or a circuit, it's not possible. Whereas 2, it has even degree vertices, all the 5 are even degree and there are no odd degrees. And we see that the circuit itself is possible. Wherever you start, you come back to the same vertex. And the third one, there are 2 vertices with odd degrees and the rest are even. And over here, you get a path, an Euler path, if you start with either with A or B. So this, if the children can just write out this table and fill it up and do a little bit of thinking, and then the why of it. So then we realize that a path, always if there are the odd number of vertices, odd degree vertices are either 0 or 2, only then a circuit or a path is possible. Even degree vertices can be any number. And if the odd degree vertices are 2, then you have to start at that point, one of those 2 vertices, to complete it. So the reason is a path that leads to a vertex. Here I'm telling you the reason, but it's nice to find out. A path that leads to a vertex by one edge, it has to come out through the other edge. So the edges, they come in pairs, even numbers. So you can have any number of even vertices, it doesn't matter. You can just still keep going around. But then the start and the end point should have an odd degree, can have an odd degree. Any other vertex, if it has an odd degree, then you're stuck. You can't proceed. So the number of odd degree vertices can be only 2. And if it is 0, that is, there are no odd degree, then you get a circuit. So this is
Ma'am,
what.
Ma'am, I didn't get it. Can you please explain it again? Odd degree vertices and even degree vertices and the pair of vertices, what you have said.
Yeah, so if you start with degree, like say the figure 2, right? You start at any vertex, then you go to the next one through any path, yeah? And then you come out of that vertex through any other path. So they are always in pairs. You go into a vertex, you come out of a vertex. So like this, they are in pairs. And so even number of vertices can be any number, as long as you can go out and come in, you can go out and come in. But then if it is odd, you have to start at that point and then just leave that vertex, right? So, or reach that vertex through a path. So the odd and the, if you can have only 2 odd degree vertices. It's either to have a path. If you don't have any odd degree, it's fine. That is fine. But it's either 0 or 2 in order to have either a circuit or a path. I think we need to try it.
Yeah, I've done
it, and then
yeah.
if we will not clear, then in next class we will ask it.
Yes, yes. That will be so nice. If you can try it out and ask, we'll be really happy.
Yeah.
Please do.
I've tried to put some arrows and all. I don't know whether that makes it clear or worse.
Yeah.
You see, there is this one vertex which is blue in color here.
Yeah, yeah.
So there is an entry, there is an exit, there is an entry, there is an exit. Right?
Yes.
So you can always exit out of this because there are even number of edges which are touching that particular vertex, because therefore you can say that I can enter and I can exit through a second one. I can enter from a third one and exit through a fourth one. Okay.
Got it,
Whereas
sir,
if you
got
look at the thing B, I can enter, exit, and last one I can enter. That's about it. After that, I can't exit. The third one, once I enter, I'm stuck there. Okay, I can't exit it. So the maximum I could have is 2 of them where those are dead ends, in the sense equivalent of a dead end. I mean, where I can enter, exit. So all the events I can sort out and remove it. But the moment there are odds, there are only 2 odds which are available. I mean, 2 odds which are possible.
Yeah, so figure 3, if you start at A, you'll finish at B. If you start at B, you'll finish at A. And you have to start or finish at A or B. Only then you can do, that you can have a path. So the start vertex and the finish vertex are very important in 3. Whereas in 2, you can start and finish anywhere. It's always a circuit because you don't have any odd degree vertices.
Can go like this.
It means if we have odd degree vertices, we must have to start from any one of them and end also any one of them.
Yes, exactly.
And where we have even number of even degree of vertices, we can cross any number of time and we can start from any of those vertices, right?
Yes.
Exactly.
Yes.
Exactly. Beautiful. Yes.
Thank you.
Yeah.
Thank you. Thank you. Yeah. So with this, there are a number of similar puzzles and problems associated with graphs. So the very famous one is a traveling salesman problem, where you have to, there are many number of cities which are connected by roads, and then you want to visit every city here exactly once. So here it's the other way around. The paths, the edges, you can go any number of times, but in the cities you have to visit only once. And the graph is weighted, so the distance between the 2 cities, or maybe how long time it takes to travel between the 2 cities. Those are the weights that are put, like 10 and 30 and all that so Google Maps is going to use something similar for you to find the route, the best possible route, right? If there's a congestion, it takes greater time, so it shows you a different route, saying that this is better. You have to give all the different places you want to visit one after another, and it tells you the best possible way to visit all of them. So that is the thing. And a similar, we have a Chinese postman problem or the route inspection problem, which is same thing as your your Königsberg Bridge problem. Over here, you want to go through all the edges once and only once, but then the edges are weighted. So you make sure that you know which are the, but then and once again you try to have a minima, like maybe you find you want to go through all of them once, but then you want to make sure you're going to have the sorry, you want to take the shortest route among all the possible routes, if such a shortest route exists. So, and here it depends, once you weight that particular graph, it depends where you started. For the last one, for example, you want to start at C so that you go through all the different, and then you might be going through B and C 2 times. So that is also okay. The blue line tells that I'm going to go between B and C 2 times. Because if I want to go through all the paths, then I want to have the minimum cost or the minimum weight, then 8 is the 8 cost between B and C is what I would like to traverse 2 times. So you have many variations of these kind of puzzles.
These are hugely practical problems in terms of courier services, and even today in a more recent time, if you think about how Amazon will be handling whether, of course, it's not exactly the same problem of a traveling salesman, but in terms of where do you locate your hubs, where do you locate your the distribution centers and stuff like that, it's all about that optimization, minimization problems. All these kinds of problems are the ones which are the basis for solving those real-time problems.
Yeah. So you can model so many things using graphs, right? Molecules can be modeled. The bonds between the molecules are the edges in your graphs. You can model, this is what Google also uses, like, Google Plus and Facebook and all that. It shows you all the people who are connected as friends. And so many times Facebook asks you, like, so-and-so may be your friend. Why? Because they have a common edge. And then you can show the phylogenetic tree or the evolutionary tree using these graphs in hereditary relationships as shown in the center. We have airline routes connecting different cities. So all these are different kinds of graphs, applications of graphs. So now we come to a different kind of a puzzle, and it's again interesting for children because it involves coloring. So this is called the map coloring problem. So here on the right, you show the map, you have a map of India, you have all the different states that are colored in different colors. And they're colored in such a way, if you notice, that if the states, they share a border, they don't have the same color. So for example, the states that border Karnataka is in pink, right? So Telangana is in orange, Andhra Pradesh is in green, Tamil Nadu is purple, Maharashtra is also purple. That's okay because Maharashtra and Tamil Nadu, they don't share a border, so they are both in purple, right? So overall, we see that 5 colors have been used over here: pink, orange, green, yellow, and purple. And so here is the question or the challenge. Do we need 5 colors to color this map? Or is lesser than 5 colors sufficient, right? So meaning that no 2 states which share a border should have the same color. That is the constraint. Is lesser than 5 enough? Can we do it with 4 colors? Can we do it with 3? Yeah, next. So this is what we call as a map coloring problem. If we look at a subset of the previous India map, we see that 4 colors, like for here we have Karnataka, Andhra, Kerala, and Tamil Nadu. We see that 4 colors are involved. But then we can also do it with 3 colors because Kerala and Andhra can have the same color, they're not touching. So any kind of map, okay, what is the minimum number of colors you need to color maps? In such a way that the areas that share an edge do not have the same color. And this we call as the map coloring problem.
There are 2 people, Suvarna, Levita, and Namita, who have said 3, Bama.
Yeah. But yeah, we can come up, we can try drawing a map. So this is an activity you have to give the children. So they will come up with all kinds of maps, very imaginative ones, okay? And then you have to challenge them. Okay, this map requires 3 colors. Now can you draw a map which requires 4 colors? Can you draw a map that requires 5 colors and so on? So you ask them this and it's very nice. So yeah. Next, please. So in order to find the minimum number of colors to color a map, we first simplify a map in the following way. So you can imagine a map that is drawn on a piece of paper that can be a piece of rubber, right? That can be stretched. And so which means that all the squiggly borders between the states, okay, that can be straightened out, say. And so these 2 maps are considered to be homeomorphic. Homeomorphic is the word. So shown on the right. Okay, so as you can see, like here, the states that touch each other, the borders, they don't change. So Karnataka is going to touch your Andhra, Tamil Nadu, and Kerala, but Andhra and Kerala still not touching. That doesn't change. Okay, so and this branch of mathematics where we can move things around, we can deform things by stretching, twisting, crumpling, and all that, bending, but you should not cut. You should not open, you should not tear, you should not glue. That branch of mathematics is called topology. And this comes under that. So as you can see in this particular map, even though 4 colors are used, we can do it with 3 colors because Andhra and Kerala can be the same color. So here we started the map, and then we ask the children, very simple one, ask them to color. They use all different colors and color, and then you can show them that it can be colored in 2 colors. Ask them the question. Use the fewest number of colors. You tell them. Then this particular map, you need only 2 colors. And next, now we see, okay, now we try to make it a little bit more complicated. We add a little, an area, okay, and extra area is added. It touches both the green and the red areas, which means that this new area which is added, you can't color it red or green. So we have put a new color that is yellow, right? So this map requires minimum 3 colors. Now what do? I make it a little bit more complicated. I try to draw a bit of area on the top, which is going to touch my yellow, my red, and my green, right? Squares. So that particular area, now you can't color it green or red or yellow. It has to be colored a different color. So here I have chosen purple. Now try to add an area which is going to touch all these 4 purple and yellow and green and red, and see what happens. Yeah. So now that I add that, so do you really need this 5th color is what we have to think. But then you see that bottommost on the left bottommost red can be colored yellow, right? And if we do that, even though this initially touched all, we can color this new area red itself, right? We don't need a 5th color. Okay, so that is what is so nice. I mean, yeah. So once we do that, we start thinking, do we really need a 5th color, or are 4 colors enough to color any map? So there was a South African mathematician called Francis Guthrie, and he made this 4-color conjecture in 1850s. And people were trying to prove this, that for any map, only 4 colors are sufficient. But then it took more than 120 years to prove and in only 1976, somebody could prove it, Apple and Haken, and they used the computer to prove it. 1,200 hours of computer time, so the proof is very difficult. Just that 4 colors are enough. And initially, this proof was not accepted because they used a computer, but now it is accepted. So now between Europe, as shown on the left, can be by using topological, just you make this edges straight and all that. It can be, it's the same map shown on the right in the black, and the same thing can be made into a graph as shown on the rightmost. So what does the graph mean? The vertices are the different countries, and the edges represent those countries that share a common border. So Poland and Germany, they share a border. So there's an edge between P and G, or shown on the right. So all these three represent the same things, different ways of representing them mathematically. Yeah, so these are different examples you can give the children, and then ask them to come up, first color them with minimum number of colors, and then ask them to come up with a map. So initially, don't tell them that 4 colors should be sufficient. Ask them, is it possible to come up with a map which requires more than 4 colors? And they can do it in pairs. They can share their maps, and each one can challenge the other one. The kids can, it's a lot of fun time they can have. And they learn a lot in the process. Thank you.
These are some of the maps we have to prove that it can be done with 4 colors, no, Bama?
Yes. Yeah. Thank you.
The 4th one looks really complex.
Ma'am, this activity that we have just done, it's about the vertices, which are joining so that they are disjoint with the help of the colors, and we can identify them. So what all, I'm just asking as a newcomer, how can we, which all levels are to be taken up, which grades? Like
grades,
6, 7?
is it? Okay. Yeah. Even from 5th grade, they start to enjoy it. 5th, 6th, yes. You can do the map coloring, definitely we can do the map coloring with them. And the other one, the taking out, even those, all these middle school level is very nice. Middle school is very good for, they enjoy.
Okay, ma'am. Thank you.
Yeah, thank you. I think I've taken too much time. 5 more minutes.
No, we knew we will be overshooting by a few minutes, Bama, today. Yeah.
It's 7 minutes. That's all right.
Yeah.
We've come to an end, I guess. So, does anyone have any questions to ask? I guess not. Thank you, Bama ma'am and Ramesh sir. Thank you for the session, and thank you all for joining.
Yeah.
Thank
you. And the next session is before
next
Diwali,
Friday,
right?
sir.
Okay.
We don't
3rd,
have.
I'm going to be on a flight. I'll figure out. We'll figure that out. Between Sendil, Bama, and myself, we'll figure it out. I'm on a flight on the 3rd.
Oh, is it?
No, I think Smith. Okay, we'll figure it out.
Yeah.
All right, then we'll end the session for today. Thank you all for joining. Bye. See you.
Okay. Thank you.